Alright, so we're going to cover Unit 7 Waves, Notes 2, Practice Problems Part 2. This is going to focus on practice problems 8 through 19. So let's go ahead and get started with number 8, which says a sound wave produced by a clock chime is heard 515 meters away 1.5 seconds later. What is the speed of sound of the clock's chime in air? So the first thing we want to do always is to write down all the data points that we have. So I have two numbers in this problem. We have 515, that's in meters, and then 1.5 seconds. So let's determine what those are. We know that meters is a measurement of distance, so that's my distance, and then seconds is a measurement of time, just like that. All right, if you remember from the lecture, there's a speed equation that calculates the speed of pretty much anything. You can use this equation to calculate the speed of anything, but for the speed of sound, it's going to be the distance divided by the time. So in this case, speed is equal to 515 meters divided by 1.5 seconds. So if we did that equation really quick, our solution would be that the speed, or in this case, let's go ahead and write v for velocity. Velocity and speed, you guys for now can just understand that they're kind of synonymous. It's kind of the same thing, velocity and speed. It's going to be 343 meters per second. So that's the answer for practice problem 8. Practice problem 9 says a wave has a speed of 9.0 meters per second and a wavelength of 3.0 meters. What is the frequency? So let's go ahead and write down some numbers. We have 9.0 meters per second, and that is our speed. And again, we're writing speed as the letter V now. And wavelength is this lambda symbol, and that is going to equal to 3.0 meters. And frequency, well, we don't know. That's what we're looking for. But we do have an equation from our notes 2, part 2, which said that the speed of a wave is equal to the wavelength times the frequency. So we have two of those numbers, so let's go ahead and plug those in. So we have 9.0 for the speed, and that is equal to my wavelength of 3 times my frequency. So if I rework this equation, frequency is equal to 9 divided by 3. In that case, frequency is going to be 3, and then the unit is hertz, Hz. So that's practice problem number 9. Practice problem number 10 says the speed of a transverse wave in a string is 15 meters per second. If a source produces a disturbance that has a frequency of 5 hertz, what is the wavelength? So again, we're going to start off the same way. We're going to write down every single piece of information we know. We know that we have 15 meters per second. That's the number that we have. And the other number that we had was 5 hertz. All right, so let's go ahead and identify what those are. That's going to be a velocity, and that is going to be a frequency, right? And the question is asking for what is the wavelength? So what is the wavelength? We don't know. But remember the equation that we just saw in the previous problem and in the notes. V is equal to wavelength times frequency. So what you're going to do is just take these values and plug them in right into the equation. So 15 for V, 5 for F. So 15 is equal to my wavelength times 5. Therefore, wavelength is going to equal 15 divided by 5. And so my wavelength is going to be 3. And then you might ask yourself, well, what's the unit? The unit here, since the velocity was measured in meters per second and frequency is measured in cycles per second, the seconds cancel out so that you have a wavelength of 3 meters, and that's what's left over. So that's practice problem number 10. Practice problem number 11 is actually a pretty easy one. It says, what is the shape of all of the waves in both graphs? Well, if you recall from notes 1 in this unit, we covered the different shapes of the waves. We have transverse, longitudinal, and surface wave. And the one that goes up and down like that is known as a transverse wave. So all of these waves here, in the 3 in this graph and the 3 in this graph, every single one of them is a transverse wave. Number 12 says, which wave carries the most energy in graph A and why? Well, you can kind of see that these waves have something in common for both graph A and graph B. And the thing that they have in common is that they all have the same wavelength. And you can see right here that the waves start at the same point, their midpoint is at the same point here, and then they also end at the midpoint here, and then this is the beginning of another wave. The only thing they have different is the height, and the term for that height is called amplitude. So the thing that changes here is the amplitude, and that actually does affect the energy. Remember that the higher the energy, the higher the amplitude. So actually, let's reverse that. The higher the amplitude, the higher the energy required to produce that. So which wave carries the most energy in graph A? It is wave 1. It has the highest amplitude. So I'm just going to write down highest amplitude. Right. So that's number 12. Moving on to number 13. Which wave carries the most energy in graph B and why? Well, we have wave 4, wave 5, and wave 6. It doesn't matter if wave 6 is going down. If it was lower than negative 1.0, it would have had the highest amplitude. But since wave 4 goes all the way to 1 and then negative 1, that has the highest amplitude. So it's going to be wave 4. For the exact same reason as the previous question, highest amplitude. All right, number 14. What is the amplitude of wave 1 in graph A? Well, we want to make sure that we're calculating from this midline here. So I'm going to actually pull out a straight line tool. So we want to go from this midline right there. Actually, let's make that red so that we can see that. To the very height. So we're going from that midline to this height right here. And we want to measure that. So if you take a look at the y-axis, you can say that it's 1, but 1 is not a good enough answer. So we can't just say 1. We have to also include the unit. So that's when we have to read the axis here. So it's 1 centimeter or 1 cm. That is the amplitude of wave 1. Number 15, what is the wavelength of wave 6? All right, so wavelength of wave 6. Wave 6 is going to be on this part of the graph, and it's going to be measured from this point here to this point here. I'm actually going to do something kind of interesting here. I'm going to draw a line from this point to this point, and then I will be able to drag that line on anywhere on that wave 6. So notice if I follow this line anywhere, it's hitting this line is hitting this point right here and this point right here. And if I am just following this point right here, let me see if I can select just this line. There we go. It's following in both spots. So if I go trough to trough or midpoint to midpoint, or over here I can go midpoint to midpoint, it's hitting the exact same spot. So I'm just going to go trough to trough because that's just good convention of how to measure wavelength, or crest to crest. And it's going from 2 to 10. So we want to measure that distance from 2 to 10. So that is a difference of 8. So that's a 8, and then we have to read the axis, 8 centimeters. So that's the wavelength. Number 16, list 3 characteristics of a wave that you can take measurements of. Well, we can take a measurement of the amplitude. You can also take a measurement of the wavelength. And the final thing that you could take a measurement of, in these graphs, you wouldn't be able to take a measurement of anything except the wave height, which is going from here to here, from crest to trough. You can take a measurement of the wave height. But another thing that you could take a measurement of would be the period of the wave, or the frequency. So either write down frequency / period. And you do that just by counting how long it takes for a wave to pass a certain point. All right, number 17. What is meant by frequency of a wave? What are the units that are used when it is measured? Frequency, if you remember, is just a measurement of how many, the number of waves divided by how long it takes for those waves to pass by. So the number of seconds. Another equation for frequency that you could use is 1 over the wave period. The other equation that we also learned before, if we take this equation, V equals wavelength times frequency, you could say by rearranging this that frequency is equal to the velocity divided by the wavelength. There are 3 different equations for frequency. So the most common one that in the literal term, if you're just defining what frequency is going to be this one. And the units for frequency are hertz, Hz. So the unit is hertz. Okay, so that's number 17. Moving on to 18. If the frequency of a given wave increases, what happens to the wavelength? Well, you might have an equation like this. V equals wavelength times frequency. So we have these two things. We have the frequency and we have the wavelength. So we needed an equation that ties in both of them. That's why we're using this equation. We have the frequency here and the wavelength here. So we have both of these equations, tied those in. And the question is asking, what happens if we increase the frequency? Let's just play around and put in some numbers. So let's say I have my wavelength is 2 and my frequency is 4. Therefore, my velocity would be 8, right? So 2 times 4 gives me 8. But if I have 2 times 5, so let's say I increase the frequency, then I have 10 as my answer. But here's the thing. In a given medium, in any given medium, the speed of sound does not change, or the speed of a wave does not change. So just because someone's pitch of voice is changing, that doesn't mean that it's traveling faster through the air. Through the air, the speed is going to remain the same. So V has to be a constant thing. So let's try these. Let's try new numbers here. Let's try 3 and 4, right? So if my wavelength is 3 and my frequency, actually let's reverse that. Let's do a wavelength of 4 and my frequency is 3. So I'm just going straight down here, right? So there's my wavelength, there's my frequency. What is my velocity at that point? It's going to be 12, right? And just as I said before, that can't change in a given medium unless you change the medium itself. So the way you can increase the speed of sound, for instance, is if you change the composition of that air that it's traveling through. So if you have more or less oxygen, like if you're up in the mountains or down at sea level, or if you change the temperature of the air, then it's going to change the speed of sound. But in any given room or a scenario where the temperature is the same and the air composition is the same, the speed of sound is always the same. So let's assume that this number doesn't change. So we have 12, all right? The question asks, if a frequency in a given wave increases, so let's increase the frequency to 4, what's going to happen to the wavelength? Well, the wavelength is going to decrease if the frequency increases. So they're inversely proportional. If one goes up, the other must go down. And that's always going to be the case with frequency and wavelength. Last practice problem says, 19. Fill out the following table by describing how you would measure the following wave characteristics for the types of waves shown below. So how would you measure the wavelength on a transverse wave? I'm actually going to use the keyboard for this because there's going to be a lot of typing involved. So I'm going to decrease this size, and then I'm going to make sure it's not bold and just type red. For wavelength, there's several ways you can do this. Crest. Just let's make sure this is red here. Come on. There we go. So you can do 1 crest to crest. Another great option is trough to trough. All right, so those are the only 2 scenarios that I would feel comfortable with you using on a test or a quiz of how to measure wavelength. You could measure from different points of a wave as long as they're the same part of a wave, but that gets a little bit tricky. The easiest ways to do it are to do crest to crest or trough to trough. For compressional wave, how do we measure wavelength? Well, you measure it from the beginning of one compression to the beginning of another. So if you have two compressions, you measure from the beginning of the first one all the way to the beginning of the second one. And that's how you find the wavelength of a compressional wave. Talking about amplitude for a transverse wave, amplitude is measured from resting position to either crest or trough. So it doesn't really matter which one you measure to, whether you measure to from the resting position to the crest or the resting position to the trough. The number should be the same. You might get a magnitude that's either positive or negative, but the actual number itself should be the same. And then finally, the amplitude in a compressional wave is going to be the width of the compression. All right, so what I'm going to do now is kind of draw pictures to kind of emphasize what I'm talking about there. So if I do a wavelength here, so if I just draw a simple wave here, I can either do from crest to crest or trough to trough. That's going to be a wavelength. For a compressional wave, you're going to have your, let's say you have a compression and then a rarefaction, and then another compression and then another rarefaction. So the wavelength is going to be from the beginning of the first compression all the way to the compression here. All right, for the amplitude, for a transverse wave, we have, let's go ahead and draw another transverse wave. Close enough. And the amplitude is actually going to be measured. Let me draw actually a baseline here, going straight through the center here. The amplitude, which is going to be in green, is going to be measured from the baseline to the crest or the baseline to the trough. It doesn't matter which one you use. So the amplitude is that measurement. And then finally, for a compressional wave, if we draw a compressional wave, we have a compression here and then a rarefaction. So, and then another compression and a rarefaction. All right, and the actual amplitude is going to be the width of one compression. How much is that compressed? So that's how you measure that. All right, so that's practice problems for notes 2, part 2, 8 through 19.